Students, we should begin lecture number 9. I welcome you all for this lecture. So, we will carry forward discussions on mechanical behavior of materials, but initially as usual we are going to have some recap. So, as I said, we are going to learn about the basics of material science engineering in the first 7-8 lectures. So, correlation between processing structure and property is the fundamental aspects of material science engineering. This is to be learned at the beginning, because if you know this aspect, then only you can use this concept to design and develop new materials using machine learning and artificial intelligence. So, this has been shown by these two pictures in a very nice manner. First one on the left side is what is called as a materials tetrahedron. I talked about in the last lecture, and this tetrahedron has 4 points as usual, and each point indicates important features of material science engineering: processing, structure, properties and performance. We have to make things, and if you want to make new things or whatever existing things also, components or pieces or devices, whatever you talk about it, you need to process them. So, you have to add processing routes and parameters to achieve that, but that is not the only thing, because processing dictates the structure or the microstructure or structure of the material, and this in turn dictates the properties. And finally, what you are looking at, just like any exam, your performance is important. Finally, when you look at any device, it is a performance of the device which is very important. You will always like to buy the best phone in the world at a price which you can afford. So, therefore, performance of the phone is important for you. Same thing is true for material system. So, performance of material systems is what dictates their applicability, and performance depends on properties which are available, and the properties depends on structure, and in structure depends on processing. To understand the structure, we need to do detailed characterization. That is why the red or the rather ball which is at the center is characterization. Characterization is the tool which allows, or they consist of tools which allow you to determine the structure of the materials which you produce. On the right side, you see I have listed some properties, not all, and you can see I have listed brittleness, that talks about mechanical properties which we have been discussing. Then I talked about ability to pass light, here you can see that talks about optical properties of material. Magnetism, which is basically magnetic properties. Flammability is basically ability to burn, and then toxicity. Toxicity is very important for biomaterials, right, which you are using in our, you are going to use in your body as an implant. And then corrosion. Corrosion is very important functional properties, because we lose a lot of material because of corrosion happens in the world. Seawater is one of the worst corrosive agents in the world. So, if you want to use a sea vessel, what kind of material you will use? And then you have other things like state, solid, liquid, gas, or physical appearances. These are some of the properties. Other than that, you have many other properties, but each of these properties are connected with structure, and structure connect with processing. I talked about it quite a lot of this aspect in the last lecture. I thought of giving you a whole perspective so that you can get a clear connectivity between these 4 pillars of the tetrahedron. And so, we are going to discuss about mechanical, and at the end of the lecture we will talk about some of our physical properties, and further we will continue on these aspects in the next lecture also. Mechanical properties are what? That depends on the loading conditions, am I correct? Whether you are loading by tensile, compressive or shear, that will dictate what kind of materials you can use. Obviously, they will not be same, right? One material cannot perform best under all conditions. If you think of the the structures or the houses or buildings, the pillars which are used to take the load, they have a huge compressive strength. That is why all the cement companies, they advertise massive compressive strengths which can be provided by the cements, right. So, compressive properties are not same as tensile properties. A material which will fail miserably in tension may not fail at all in compression. Shear, which is very important for various kinds of machines which are components which undergo shear kind of loadings, and they can fail in shear, may not fail in tensile. So, therefore, depending on the type of loading conditions, material properties or mechanical properties of material may change, and that you must consider. So, we are talking about tensile properties mostly here, because that is what gives you the best properties possible. But remember, tensile testing provides mechanical properties of what? Metallic materials, which are having such reasonable ductility. Compressive properties, compressive test or compression test rather, are best suited for ceramics or brittle materials, because brittle materials will miserably fail under tensile loading conditions, but compressive loading condition will allow them to show some ductility. And in tensile test we use UTM or universal testing machine. I talked about it last class. The most important aspects of tensile test machines are basically load cells and extensometers, and after the tensile test you get a plot between the stress versus strain. Remember, your raw data is not stress and strain, raw data is load and extension. Okay, load cell and extensometer gives you load extension. You have to convert this data into stress versus strain, and stress is nothing but load by area, and we have two types of stress, engineering stress and true stress. Engineering stress is given by the load divided by the original area of the specimen or sample. True stress is given by the load divided by the actual area of the sample. The strain is obviously two types, engineering strain and the true strain. Engineering strain is given by delta L by L0, where delta L is the change in the length and L0 is the original length. The curve will look like this. Initial part of the curves provides you the elastic behavior, that is why the elastic properties are measured. Hooke's law will be applied. You can clearly see the stress and strain are proportional to each other. So, therefore, this particular part of the curve behaves nicely, Hooke's law, but after a certain level, that is called yield stress, which is shown here, the material undergoes plastic deformation and then it reaches maximum stress which can withstand, that is called UTS or ultimate tensile strength, you can see here, and finally material fractures. So, therefore, there are two domains, one elastic domain, other is a plastic domain, and so this must be taken care of. Many materials will not show this demarcation very nicely in terms of yield stress. So, that is why for that we have to use a different approach to find the yield stress or proof stress, and we always take 0.2% offset and draw a line parallel to the initial portion of the curve. Wherever this line will cut this plastic portion of the curve, that is what it dictates you the proof stress. Well, I will not want to discuss much of this. I have already talked about it, yield strength, Young modulus, UTS, ultimate tensile strength, and the proof stress, which you probably have understood by this time. So, in a tensile test, what you do? You take a piece of sample which is dog bone shaped and start pulling it down. For a layman's language, that is what you do. You take a sample and pull it apart, and as you pull it apart, sample undergoes elastic followed by plastic deformation. And in the elastic deformation, if you unload, it will material go back to its original shape and the size. In plastic deformation, material will never go back to its original shape and size. Material will deform initially uniformly, and after some time deformation will be concentrated to a small part of the sample, that is called a neck, and there only all the deformation will be concentrated and material will fail from that region by formation of a crack or fracture. That is what is shown at the end of this test. So, this 1 to 6 is going to provide you snapshot of what can happen to a ductile material during a tensile test. Well, this is exactly shown here again, but in terms of a nice depiction of the dog bone sample, and you can clearly see what is happening to plastic and elastic portion and what actually happens when the neck forms. As soon as the neck forms, the deformation is plastic deformation is basically primarily going to happen at the neck, and that is called non-uniform plastic deformation, and after this neck will elongate and fracture. So, the length is denoted by the small letter L here, okay, compared to the past one. Last slide, length was denoted by capital letter, here it is denoted by small letter. And this is the neck. Neck can be localized, also it can be diffuse also, and necking is very paramount importance for this thing. You also need to detect ductility. Ductility can be measured by using elongation as well as reduction area. Elongation to fracture is basically very simple, final length divided by this initial length divided by the final length minus initial length LF minus L0 divided by the initial length L0, and reduction area is exactly same, initial area minus final area divided by the initial area. Remember, area is decreasing, length is increasing, that is why the formula has little bit changed. Reduction area is very generic because specimen size effect does not change the reduction in area, only the length will depends upon specimen size. So, therefore, it is better to calculate ductility using the reduction area in any kind of test which does not use the standard specimens. As I told, there are two types of stress, two stress and the two strain. Two stress is given by what? The area load divided by the instantaneous area or the actual area. Similarly, two strain is given by the total length change divided by the instantaneous area. You also remember this factor, the volume does not change, so therefore, you can determine these relationships from initial to the actual area using this formula. Well, more accurate things, okay, fine, and we can always find a relationship between two stress and engineering stress, that is not a big issue. You yourself can do this mathematics and find out. And then you can clearly see the two stress curve will be going above the engineering stress strain curve, it will never bend and it will show a continuously increasing stress strain behavior as compared to engineering stress strain behavior. Well, I like to show you that this book is very important. You can actually read this book if you are really interested, by George Dieter, Mechanical Metallurgy. This book I have followed when I was a student, still I follow as a professor. So, you can understand this is like a bible on mechanical behavior materials. If you want to learn more, please read this book. This is available even in online stores, you can purchase, it is not very expensive. Well, now comes that elastic portion is basically straight line and it follows Hooke's law. A plastic one is a non-linear curve, and therefore, we need to fit that curve with the equation, and that equation is known as a flow curve. Flow curve is given by stress equal to K into strain to the power exponent and exponent n, and K is known as strength coefficient, n is known as a strain hardening coefficient. This is a very fundamental equation, you must not forget this equation ever, because this is what will be used as a feature in machine learning. Okay, many of you will use that, and that is why this equation is very fundamental, because here n and k are material properties, and that is you require to find them out from the books for different materials, and that is what we can find out relationship between stress and the strain. Well, one can find out n and k values very easily for any standard material simply by taking log and making a straight line plot, you can easily find out. And then I talked about another two important parameters, which are called resilience and the toughness. They are ability to absorb energy. Ability to absorb energy in the elastic domain is called as resilience. Elastic domain means during the where the Hooke's law is applied, where ability to absorb energy in the plastic domain is called toughness. This is very important because material may undergo impact loading during service and they need to withstand. It cannot fail actually, if it fails then it is over. So, to withstand that kind of occasional stress above the yield stress without failure is desirable, and that is desirable in many structural applications. We can talk about component machines or even many other things. That is why toughness is very important, right. So, we always say some person is tough. Some person is tough means he can absorb a lot of occasional stress, and stress is very common in human life. So, when you are subjected to stress and you must have the ability to absorb the stress, then only you can perform, otherwise you may land up into some other difficult situations. So, materials are also similar. Materials also do behave in the same way. If you have a materials and you apply occasional impact, sudden increase of stress, then it has to withstand that. That is what is determined by this toughness. And we probably know about spring steels, I talked about it, they have very high amount of silicon, so provide you very good resilience. Well, I do not want to talk much about that, except that materials should not behave like a brittle fracture where it fails miserably, but it should show ductility that can be determined by looking at the fracture surfaces after the tensile test. Temperature has a strong effect on the mechanical properties. Temperature will allow, increase of temperature will lead to increase of ductility, but increased temperature also will lead to drop in the yield strength as well as tensile strength. This is very important for superalloys, we talked about it. So, superalloys behave completely opposite. There is an anomaly for the Ni3Al based alloys and nickel aluminum based alloys. Actually, the yield strength increases at a certain temperature range at high temperature between 500 to 700 degrees Celsius temperature. There are reasons for it. That is why superalloys are workhorse for the aerospace industry. So, this behavior is very typical one, but there are exceptions also. And this is the one for steel, actually mild steel. As you see, as you decrease the temperature to liquid nitrogen 1, the strength increases, but it becomes more and more brittle, or ductility rather it decreases. I would not say brittle, ductility decreases substantially. But you know, there are many applications where you need to use the material under liquid nitrogen conditions, and there you need to provide materials enough ductility to withstand this kind of impact loading of failure due to some kind of a stress. So, BCC metals are actually very bad at low temperature. They normally fail very miserably at low temperature. FCC metals are not. That is why stainless steel is a wonderful material to use at low temperature, but not normal mild steels. Mild steel has a BCC structure, they fail miserably. You can do this test very nicely. You take a mild steel rod and then put it in liquid nitrogen, it will break or it will be behaving like a brittle. But if you take liquid nitrogen in a mug made of stainless steel, it will not break, because it has FCC structure, and it can have still ductility at liquid nitrogen temperature. You can see nickel retains almost 80% ductility at minus 200 degrees Celsius temperature, which is massive, and ductility does not change much if you go from minus 200 to a plus 800 degrees Celsius temperature. That is the beauty of FCC materials. So, if you want to design materials for low temperature application, this factor of crystal structure you must keep in mind. So, let us start with this is very important for you to know, that is what I thought I should elaborately discuss. Now, materials also undergo deformation at different rate, and that is what is called strain rate. Strain rate means what? I can apply load at different rate, right. I can apply load at a slow way, I can apply load in a very mild way, or I can apply load in a fast way, right. When two cars collide, the load applied is very high at a small time. So, that time factors comes into picture, that is what dictates the strain rate. Strain rate is defined as d epsilon by dt, and what is that? Epsilon is basically strain and t is the time. So, that differential of d epsilon by dt is what is called a strain rate. And if you look at carefully, strain rate has a strong effect on the tensile strength. So, tensiles of the material at room temperature does not behave, much change happens as a function of strain rate, but if you have to increase the temperature, this behavior becomes very strong, or that the dependence on the strain rate is very important. This will be very clear why this is important when you discuss about the deformation processing, by which you can prepare different kinds of objects like fan blades, sheet metals, or even bars, all these things we will talk about it. So, this is typical behavior of tensile stress versus strain rate as a function of temperature for steel actually. So, now we can actually put another equation, and this is what you should focus on, because these equations are what going to provide you the means to model. When you develop a machine learning model, these equations are very important. So, stress is equal to constant C multiplied by strain rate to the power m, and you see there is something called epsilon and t. That means what? This equation is valid as a constant strain and temperature. Here m is another exponent, it is called strain rate sensitivity. Remember these aspects. So, it talks about how strain rate can change the stress. That is the exponent. It is not a linear equation, right. Epsilon sigma is not equal to, I should rather write sigma t, not sigma, because other these things will become difficult for you to understand. Sigma t is equal to C epsilon dot to the power m. It is not a linear, it is a very highly nonlinear equation. M is a strain rate sensitivity. It has very strong role. This is also material parameter like n. So, you have seen n and k, right. Now, you have seen m. These parameters are actually fundamental material properties for mechanical behavior of materials. So, as you can clearly see, m depends on epsilon, the strain, and the temperature. These are some of the values of m. So, what you see, for aluminum values are very small, but very high values are obtained for lead, or you can see titanium 6, aluminum 4, vanadium, which is a biomaterial. Very high values can be there, but otherwise M values are always close to 0.1 or 0.2, not more than that. And remember, these are values that obtained at different temperatures. So therefore, M is a fundamental parameter. Please remember this aspect carefully. So if you have very high values M, material can be formed superplastically. What does it mean? That means you can see this picture tells you thousands of words, right. If you see, this is tensile specimen, and you can see after deformation material has not failed at all, but it is elongated extensively, several hundreds percentage elongation is possible. Forget about 20-30%. Here elongation can go up to 1000%. That means a small piece can be elongated 1000 times. The length can be increased without any failure. This is a very complex alloy: aluminum, zinc, magnesium, copper, and nickel, and this shows that behavior. M values are very high for this. This is another alloy, commercially pure cast titanium. It also shows that you could have seen that there is a neck forming, but it has perfectly not formed, because as you know, the moment neck forms, all the deformation will be focused or concentrated on the neck region. Uniform elongation is no longer possible. So what is done? Basically, in this kind of materials, you can keep on deforming uniformly even without any fracture. Can you imagine this kind of things? Yes, there are a lot of materials actually behave this. Even some ceramic materials behave like this. So it is not surprising, but superplastic materials, plastics, as many polymers behave superplastically also. So then we talk about little bit of other two important aspects, fatigue and creep, in the next lecture, because fatigue is something which is repeated loading, and therefore let us stop the part 1 of lecture number 9. Part 2 will talk about fatigue and creep and other behaviors. Thank you.